8. We good? We're doing with respect to y, right? So x cubed is like a constant, derivative of y is 1. That's all a big constant, derivative of that's 0, and then derivative of that's negative 8, right, with respect to y. All right, do y'all want to do the second partials now? Is this working for y'all, the way I'm doing this? Okay, partial with respect to x twice. Who wants that? Go ahead. 6xy plus 24. Good. I think I agree. Who wants with respect to y twice? Ooh, that one's in. Go ahead. 0, 0, right? With respect to x, then y. Who wants that? What do we get? With respect to x, that's this. And then now with respect to y. Go ahead, Greg. 3x squared. All right, there we go. Those are our partials. That's all we need to do the problem. Now we need to set these things equal to 0. Or maybe to each other. I mean, it depends on how this works. Okay, so if I take the partial with respect to x, set it equal to 0, that turns out to be 3x squared y plus 24x equals 0. And then if I take the partial with respect to y, set it equal to 0, I get x cubed minus 8 equals 0. All right. Now, when I look at that, this is not where my eye goes. My eye goes here because this equation only has one variable in it. And that means I should hopefully be able to solve it, right? So I just move the 8 to the other side. And then I take the cube root on both sides. And when you do cube root, do you have to do plus or minus? No. So there's only one solution to that, and that's 2. So the only way that this is ever 0 is if that's 2. And for us to compute capital D, you have to find a point that satisfies both of these simultaneously. So any point I ever get here, the x coordinate must be 2. I know that for sure. The question remains, though, what's the y coordinate? Yes? You could set them both equal to each other, but I think it would be harder if you do that.
For this one in particular?
Yeah, for this one in particular. Because if you set this equal to that, then move everything to one side, it's going to be kind of tough to solve. I didn't go down that road intentionally, but when you're working these problems yourself, you might actually go down that road and then get kind of hung up. So if you do, start back at the top, try something else, right? All right, so if x is 2, this has to be the case every single time x must be 2, then can't I just go to this equation and replace x with 2? Mm-hmm. Yeah. So let me do that. I'm going to bring this down, but I'm going to let my x equal 2 go into that, right? And if I do that, then I'm going to get, let's see, 2 squared is 4, times 3 is 12, so it becomes 12y. And then plus, let's see, if x is 2, right, that's 48. Must equal 0. And now I have an equation that only has y in it. And so I think y is negative 4. A lot better than setting them equal to each other? Oh, yeah.
How did you try it? No.
You can just see how bad it would be, right? So I only have one critical point, right? The only way that you can satisfy both of those equations simultaneously is if you let x be 2 and x be 2 and y be negative 4. Questions? Shall we test it? Calculate our capital D. Capital D at an x value of 2 and a y value of negative 4 will be, okay, I'm going to write it out. I'm going to do in here, I've got to plug into this 2 for x, negative 4 for y, and then add 24, right? That's what I'm doing. I'm doing the partial with respect to x twice at the point, and then I'm multiplying that times, that times what? 0. So that all doesn't matter, does it? It's all going away. And then minus something here squared, right? which would be, if I plug in, what am I plugging in here? 2 for this? I get 12? So what can you tell me about capital D? It's what? It's negative, right? It's negative. Because 0 minus some number. So 0 minus 144. So this is a negative number, right? That's me saying negative. And if it's negative, then I can tell you right now I don't have local max or min, right? I have a saddle. But I do have a saddle. I mean, I do need to state that because it's not just some like random point on the surface. There's something interesting happening there. It's kind of going down in one direction and up in the other. So I have a saddle point at the x-coordinate 2, y-coordinate -4, and z-coordinate, I have to plug those values into that, right? And I think I'm going to cheat because I have it here already. It's, you should get 48.
I like that.
48. I'm not showing that step, but just remember the x and the y you're looking at go into the original function. So this is actually kind of a cool looking surface. I think it's cool looking. Right? It's kind of odd shape. It's kind of weird. It's like this little like slide. I just imagine like sliding down this little thing. And then here's our point. It's hard to see it. Right there is our saddle point. So like if you can imagine being on that point, it'd be like being on a saddle. Yes?
Is it parabolic, I guess, going up in those, like where it's cutting up like that?
Kind of. I mean,
going up to infinity?
It's parabolic in the sense that, I mean, we do have x squared in here, so we should expect some parabolic behavior, but we also have this behavior, right?
Yeah.
Which is like cubic in one variable, but then linear in the other. So if you put those two together, it's kind of like a 4th degree. It depends. In certain directions, it looks like a 4th degree. In other directions, it doesn't. Do you have a question?
So if you get f in respect of x and y respect, if f of x equals 0 and f of y equals 0, then it's guaranteed that you will have a saddle local min or.
I'm glad you brought that up. So what I'm going to restate what you're saying. I think what you meant is if your second partial here, right, derivative of f with respect to x twice, if that's 0, or if this is 0, then you should be a saddle. I think that's what you're saying, yes?
Well, I was saying for the step before that,
Oh.
f of x, you can solve for 0 and get a point. The other one, you can get a point. Is there ever like an exception where you will just never get a saddle or a local min or max?
Yes, there is a situation where the test would be inconclusive. And that would be when, if any of these, if this was 0 and that was 0, then everything would be 0, right? Or if that was 0 and that was 0, then everything would be 0. Or if in some way, manner, fashion, you get zeros, right, for the whole thing, then the test fails. Because the test only works when you figure out if it's positive or negative. And I believe there is a problem that I may get to today, I may not, where we're going to run into that exact scenario. And I usually offer it as a bonus question because it's not simple, but it can be figured out. So the test would fail, yes.
Wouldn't a very easy example of a formula that would cause it to fail would be a level plane?
Yeah, because
Because your second derivative is going to be 0.
it's just going to be 0. Everything's zeroed out, yeah. But then you also don't have any local max or mins, right?
Yeah.
But it doesn't have to be that. It doesn't have to be that scenario.
Yeah.
But that would be a simple. That'd be a simple example.
That's a very simple
Yeah.
example.
Yeah. Exactly. Yeah, because if you have a plane, your first partials are just constants and your second partials are zeros. All right, this one right here, that is e raised to the 4y minus x squared minus y squared. Should we look at it first? Do you want to see it first? It's the pimple function.
Oh, that's a.
It's just a pimple. That's all it is.
I wonder where the local max is.
So we can see from this picture, it looks like we're just going to get a local max, right? That's what it looks like we're going to get. All right, we got to get it though, right? You know what? I'm going to put them side by side this time. Any volunteers? Let's do them one at a time. Any volunteer? You want to go for it? Okay.
So it's just that function
Okay.
here, and then you do the partial of the powers,
Yep.
which would be minus 2x.
Minus 2x. Everyone agree? That looks good. So you have derivative of e to anything is itself, right? And then times the derivative of what's up here. So I'm going to go e to the 4y minus x squared minus y squared. And then be careful here, just, you're writing times, and then the derivative of what's up there with respect to x, which is negative 2x. That turns into, I'm just going to kind of rewrite it, negative 2x e to the 4y minus x squared minus y squared. Okay, that's our partial with respect to x. Any questions on that partial? The partial with respect to y should be very similar, shouldn't it, in terms of the same sort of procedure? With respect to y, who wants this one? Anyone want this one? Go ahead.
4 minus 2y.
E to the 4, careful. Did you say e to that, or?
I mean, yes, e to that,
E to that times what you said, okay.
4 minus 2y.
Okay, very good, yes. So e to this first, and then times down here in the base, 4 minus 2y. Y'all agree? Yeah. And now, I'm just going to rearrange this. This is just my own personal preference here. I like to put this stuff in front of the e. It does not have to go that way, but I'm going to. Okay, questions on those? I don't feel like taking the second partials right now, okay? Because I see that it's going to be a pain. Do y'all see that if I take the partial with respect to x on this again, I've got a product rule? And with respect to y here, I have a product rule as well. So I'm going to pause, time out, pause. I'm just going to go first, try and do the other part. Can I figure out when this is 0 and when this is 0? Let me do that first. Okay, so now, when is my first partial with respect to x equal to 0? Okay, well, let me take it, negative 2x, e to the, you know what? I get really tired of writing the exponent over and over, okay? So I'm just going to write e to some junk up there, right? And that's what I have. So this blue box right there is that, okay? From here on out, that blue box is that. Now this is, we want to know that's 0, right? Now the reason I don't care about that too much is because if I'm trying to figure out when this is equal to 0, what I know is that when you have multiplication, you can set each factor equal to 0. E raised to any power is never 0, right? So I don't even have to think about this ever being equal to 0, which leaves me with this, right? When is that 0? When x is 0. So there's only one solution to this. Do we all agree that e to any powers, e to anything is never 0, right? Okay. It's asymptotically approaching, but it's not ever equal. So if we do the same thing for the second one, we're setting 4 minus 2y, e raised to that junk equal to 0, then the same principle, right? That the only thing that makes that 0 is if this in front is 0, right? So that would mean that 4 minus 2y equals 0, which means that 4 equals 2y, which means that 2 equals y. So there's only one value of x and one value of y that make it true, right? That's the pimple, right? That's the actual point for the pimple. We don't know that yet other than looking at the picture. But our critical point, I'm going to put CP for critical point. Our critical point is x is 0, y is 2. That's what I have to calculate capital D of. But now I need the second partials, which I paused on because I was hoping for those to be maybe this would come out, there'd be no solution or something. I'm going to have to do the second partials. There's no way around it. So let me, if you're okay, I'm going to erase this on the bottom. Yes?
For the shift for E, for it to equal 0?
Yes.
For example, if it were to equal 0 at one point, the shift, would that be inside of E?
What do you mean, a shift?
So in order for you to do a diagonal shift from the original origin,
Uh-huh.
you would have to do like a minus H, or like, I don't know how that would be represented if it was an E. That's the question.
Well, hold on. All I'm saying is that this is never true. Like, we have to all agree on that, or else what I did isn't right. You have to agree that E raised to anything is never 0.
Yes, I do.
You agree with that? Okay, so then what's your question?
So when you have a shift, when E shifts to the left or to the right, when you do
Well, left and right, you won't change, that doesn't change. Because if you just think about what e to the, like e, just the normal e to the x function looks like this, right? Okay, if I move this left or right, you still never hit the x-axis. It goes up or down, but to do that, then this is no longer e by itself. You have to put a plus or minus here, a number, right? Which would then change what we have here, right? It wouldn't be this. So you wouldn't have a 0 over there anymore. So, okay. All right, now I'm gonna go get these partials, these second partials. Okay, here we go. Partial with respect to x twice. Okay, so I'm looking at this right here, and I'm gonna follow the same principle with this box of junk, all right? So here's my product rule. I'm gonna do it this way. Derivative of this times this, plus derivative of this times this. That's the way I'm gonna run the product rule. And I'm differentiating with respect to x. So the derivative of that's -2 times this, e to that junk up there, right? Plus, now the derivative of e to the junk, right? Which is itself, times, now you do have to take the derivative of what's in here with respect to x, which is -2x. We did that earlier, right? Are we done? No, what do we still have next to this? -2x, which finishes off your product rule. So everything you see in here, in red, was the derivative of this right side. So derivative of this is 2 times that, plus the derivative of all of this is all that in red, times finishing off the product rule is your -2x. Which, I'm going to clean this up. This is -2 e to that junk plus 4x squared e to the junk, right? Because this together is 4x squared. I put it in front. And I don't know, I can leave that. I'll leave it. There it is. Okay, just for now. Now the partial with respect to y, twice. So now I'm differentiating this one, right? And I have another product rule right here. So I'm going to take derivative of this with respect to y, which is -2, times this one, e to that junk, plus the derivative of the e to the junk, which is itself, times the derivative of what's up here with respect to y, which we had done earlier was 4 minus 2y. And then one more thing, finish off the product rule. So derivative of that, which, I'm sorry, not derivative, that's multiply times this. So it's another one of those, isn't it? So I'm just going to put squared there. And I think I'll leave it like that. Any questions on those derivatives? Partial with respect to x, then y. So going back up here, I want to take derivative of this with respect to y. I'm actually happy about that because -2x is going to be a constant because I'm differentiating with respect to y. So I'm just going to bring -2x for the ride. But there is y's up in this exponent, so that part I have to do chain rule on with respect to y. So that'll be e to the junk times the derivative of what's up here with respect to y, which we've done now, what, 3-4 times now? 4 minus 2y. What happens if you mess up? Like, what if you mess up your first partial up here? It's all wrong, right? So you got to be careful, be meticulous, take your time, right? All right, capital D. Here we go. Capital D. I don't need this anymore. I'm going to need to know what that looked like. So here we go. I want capital D at that point 0, 2, which is, okay, I've got to plug in 0 for x and 2 for y. And let's do it into this piece first. 0 for x, 2 for y. Okay, well, what can you tell me if I plug 0 for x into this one? It's gone, right? So all I really need to do is figure out what this is. Well, I need to know what happens to this thing. So let me write that down. That thing up there, this junk, right? 4y minus x squared minus y squared. What would happen if I plug into that 0 for x, 2 for y? Let's see. 8 minus, that's 0, and then minus 2 squared minus 4. So you just get 4, don't you? So I get a 4 when I plug in there. So we said here, if you plugged in 0 for x here, that's gone. Then you have negative 2e to whatever you get when you plug 0, 2 into that expression, which is this expression. So you just get e to the 4th power there, right? So negative 2 e to the 4th. That's your first part. Then fyy, this is this right here, you have to plug in 0 for x and 2 for y. Right? 2 for y. Check out what happens right here. If I plug in 2 for y right there, I get 4. 4 minus 4 is 0. That whole thing goes away, right? If I plug in 0 for y. I mean 2 for y. And then I have negative 2e to this, but don't I still get a 4 there? It's the same answer I get. So this becomes negative 2e to the 4th there. Have I lost anyone here? Are y'all keeping track of what I'm doing? Any questions? We're all right? Everyone's okay? Not done, right? Minus something squared. All right, so now that's this one, right? And when I look at this, if I plug in 0 for x, this is gone, kills that, everything's gone, right? So we just get 0. This is a negative number, right? That's a negative number. That's a negative number. You multiply two negatives together, you get a positive. And then you're subtracting nothing. So this right here is a positive number. From that, I can tell you right now, I either have a local max or a local min. So then I defer back to this first piece here. And that is now negative, isn't it? And negative, people frown. So I've got a local max here. So I have a local max at this ordered triple. It was 0 for x, 2 for y, and now our z coordinate would be whatever we get when we plug 0 for x, 2 for y here, which we've done that a few times now. That should just be e to the 4th power, which I'm just going to leave like that. Yes?
Why does the local min and max depend on the f of x power to the f of y?
That's a good question. That's a little bit it's a little too difficult, I think, for me to try and explain. But you just think about it like the second derivative from the original, like Cal 1, right? The second derivative, concave down, concave up. Just think of it that way. The thing is, you could make a similar argument, like why don't we look at fyy, right? Like why do we just look at this then? Well, somehow this formula, it actually compensates for all of that. We'd have to go look at where that formula is coming from, right, to understand. So if you like, I'd be happy to sit down in the office, we could go through it, look at the proof of the formula, and then we can see what it's actually doing, right? Like why that is such an important part of the formula. It's just, I think it's too much to try and show here. No, it's not related to that. Is there a question?
I have a quick question related to that.
Okay.
Which is, if you were to have at the end where it's that f of x then y squared, if you were to swap those around,
swap those around.
Yep.
You mean y, x?
Yes.
Would it still,
Would you then be looking at the, would you then look at your FYY? Would you get the same?
so there are different ways that you could, this formula works, but it's not the only formula. That you could come up with a formula where, you know, you're looking at the FYY and then you switch the order of the one in the brackets to YX, not XY.
Yeah.
This is just the one that we present. But there's other ways that you could like adapt this and change and switch things. There are other versions of this formula.
Okay. I was just curious, because, you know, normally if you can, if you reasonable, within reason, you could swap direction Y without affecting too much.
Well, but we also know that when you
have to go
switch
every
these, it
active.
changes the derivative changes, right? So fxy is not the same as fyx, generally speaking. All right, what do you think about that one? Oh my gosh, it's already 2:32. Wow.
Time flies when you have fun.
For me, I guess. For you, y'all are like, oh, dragon. So we have to take derivative of this. Let's see if we can get the derivatives at least. Partial with respect to x. I think what sucks about this problem is that 1 over x squared y squared part. Like that's where most people don't enjoy this problem. So here's what I'm going to recommend. That when we look at this function, that instead of looking at it that way, we look at it like this. Bring the x squared and y squared on the bottom there up and make them both negative exponents. It may make this derivative a little bit easier for us to handle. So if I do the partial with respect to x, I get 2x here, right? Plus derivative of that 0. And then here, the y to the negative 2 is a constant, right? Because I'm differentiating with respect to x. So I just need to take derivative of this. So that'll give me, actually I'm going to make it a negative 2x to the negative 3, because power rule, we have to bring the power down, subtract 1 from the power, and then like I said, the y to the negative 2 just comes for the ride. Yeah? Understand that? I'm going to take the partial of this with respect to y, and it's kind of the same thing happens. This goes to 0, that's 2y. And then on this one, this time we leave the x to the negative 2 alone, and we take derivative of this, which gives you the negative 2 y to the negative 3 times x to the negative 2. Y'all see it's like the same kind of pattern, just a little bit different on the variables? Now, I don't feel like going for the second partials right now, okay? If you wanted to, go ahead and do that, but I'm gonna go to see if I can set these equal to 0 now, all right? Remember when I started this, I said you can kind of find the way you like to do it. Some people like to get all the partials first. It just depends on you, all right? There's no one way is better than the other. I'd say if the partials are easy, maybe just knock them all out. All right, so let's set this first one equal to 0. So I need the first partial with respect to x equal to 0. All right. 2x minus 2x to the negative 3, y to the negative 2 equals 0. That's not an equation you see every day, is it? And then the other one, I need the partial with respect to y equal to 0. 2y minus 2y to the negative 3, x to the negative 2 equals 0. Nonlinear equations, right? System, 2 equations, 2 unknowns, nonlinear, solve for x and y that make both of these true. So I think what I'm going to do, let me rewrite this again. I'm going to go, this is just to make it so that my brain sees it a different way. Not necessarily sure this is where I want to go, but I'm going to just rewrite it that way because I don't know. I like negative exponents, but then sometimes I prefer the fractions. It just depends. Okay, so here's what I'm going to do. this is where everyone might go down different roads. Just make sure you do correct algebra, all right? Someone might find a more direct path than I'm going to find. Some people might take the long journey around. I'm going to combine these into a single fraction. And the reason I'm doing it is because I know that if I can get this to one fraction equal to 0, that if you ever have a fraction equal to 0, all you ever have to then do is look at the numerator. Because the only time a fraction can ever be 0 is if the numerator is 0. So I'm going to try and get it to a single fraction first. And I'm going to have a similar thing happen over on the other one. So I look at this as being over 1, and then I have to get a common denominator. So I'm going to multiply top and bottom of this by this. Okay. So I'm multiplying this first one by 1. And I want to keep that on the board over there. So if I do that and I put these together, I get 2x to the 4th y squared over my common denominator, right? And then minus 2 over the same denominator equal to 0. So I put those together, right? While I'm doing this, and I only have 2 minutes left, I'm going to do the same thing on this one. So if I do that, I'm going to get 2y to the 4th x squared minus 2 again, right, over the common equals 0. And then now, because a fraction, right, a single fraction equals 0, all I have to do is look at the numerator. 2x to the 4th, y squared minus 2 must equal 0. And then over here, if I want to look at this one the same way, this one would mean 2y to the 4th x squared minus 2 equals 0. And then what I really like here is that I can set these both equal to each other. This has to be equal to that. They're both equal to 0, so I feel the clock here. So if I set these equal to one another, right, set them equal, I get 2x to the 4th y squared minus 2 equals 2y to the 4th x squared minus 2. Those have to be equal. I can get rid of the 2's, add 2 to both sides. I can divide both sides by 2. And so my next line should read x to the 4th y squared must equal y to the 4th x squared. Any questions on that? Who wants to tell me what the next step should be? What do you?
Both sides by x squared.
Don't do it. Don't do it. What do we not divide by, right? Be careful. Go ahead. Subtract. So